Um, for those of you, I guess you got the messages that I posted that I'm not going to be in the classroom today. I'm not feeling well, and I knew this day before yesterday, so I'm doing better. I can do my grading today, so I'll get all that caught up. Um, anyway, I'm not going to come in and share it with you. Let's see. Today is November 13th, 2019, and this is the regularly scheduled meeting of ITSE 2309 at Collin College. Somebody talk to me? Am I getting out?
I can hear you.
Okay. Okay. Well, if one person can, everybody can. Oh, let's see. Indexing. Today we are looking at what module is this? It's what this. I don't think this one is numbered. This one is um, indexes, or no, this one is database objects intro. A database object is a table is an example of a database object. A view is an example of a database object. In general, we create database objects by using the create command. And so we say create table, that's an object. When you say create index, anytime you create an object, it should be in its own batch, we say. That means that there's a go immediately before it and a go immediately after it. And so it sits there all by itself. Now, sometimes you can get away without that with tables, but it's recommended that you don't try to do it. So we're going to talk today. Today, I want to talk about indexing, and and then we'll talk about some other stuff, creating sequences and the like. I have a little video here, and it's a library. I'm going to go ahead and play it. And if you can fast forward through it and watch it over here, but I'm going to turn this on for a minute. It is a YouTube. Is that volume okay?
I don't really hear much of anything.
You don't hear it? Okay, just a minute. Let me pause it. See if I can get to that. Okay. Is that a little better?
I still really can't hear it. I don't know if the sound's just like not transmitting.
Okay, so nothing's coming over the sound. Okay. Well, let me just let me refer you to it then, and we'll shut that guy down. The Two Ronnies is the confusing library, and I will let you guys. It's right on the first page of the page one of the database objects intro. And what it is that there are a couple of comedians, British comedians, are talking about a library where the books are classified by color, and big ones and little ones. So the big books are on the top and the green books are on the bottom and stuff like that. And he's trying to find the book that he wants. Well, he's looking for the title, but the books are classified by color. And this is a common, actually, no, it's not common, but it brings up an indexing problem. So remember a library. Let me go forward to where I get to the library. Next, I believe I've got it right here. Indexing. There is a tutorial on database indexing here where you can hear it from somebody else. Okay, in a library, back in the old days, when I was a kid and I had to walk to school 2 miles through the snow and all that jazz. In the library was a index card catalog of cards that would take me to the books on the shelves. And this took up a pretty good chunk of real estate in the lobby of the library where this index was maintained. And I could search on 3 different things. I could search on the title of the book, I could search on the subject of the book, and I could search on the author's name. And those were the 3 typical ones. They were color coded, I believe. And I think they have one. I don't see the colors, but here it is. Title was red, author was yellow, and subject was blue. So if I wanted to find a book that if I wanted to find the title of the book Moby Dick, I would search the title index, and I would find I might have more than one book named Moby Dick. I don't know that there are any. Author index, I could look under the author index and search for Herman Melville, and I would find all of the books that Herman Melville had written. I would find Moby Dick, and I would find 2 Years Before the Mast and stuff like that, the Billy Budd tales. If I looked under the subject index, the subject would be whales, and I would find there Moby Dick, of course, because it's about a whale. And I would find textbooks on whales, whale behavior. And so if I wanted to look at the title, I would search the title index and go straight to the textbook by author or by subject. So I could find all of the books easily by any given author. And I wouldn't have to go search through I wouldn't just go out and go looking through the title. Okay, here's an example that kind of goes to that silly video, and I do recommend, I'll go ahead and watch it. It's kind of funny, I guess. Example 1, what if I wanted to find books that contain 376 pages? I don't have an index on books containing 376 pages. I don't have that index. It's all I can do. I can search title, I can search author, I can search subject. But if I want to find books with 376 pages, I have to start at the beginning of the shelf and look at every book. Now, I'm sure that it's a piece of information that we have, so why not build an index on the number of pages? Well, the index isn't free. And if you look at what I'm saying there, what happens when a new book comes into the library? All of the data have to be updated in all 3 indexes. So if we add another index, we add work that we have to do to bring in a book or to take a book out. And the problem with it is nobody ever searches for a book that has 376 pages. It just doesn't happen. If you go into the library and say, I'd like to read a book, please, that has 376 pages, they're going to laugh at you. Nobody does that. So we create indexes that people care about. So I care about the title, the author, and the subject. Lots of people want those, but nobody wants this one with the number of pages. Example 2, suppose that we're like this definitely goes to the one. We could judge a book by its cover, and we really did want to search by the color of the cover. And let's say I want to find a red book or a blue book. Let's see, what is it? Red, yellow, and blue, I believe, and black and white. Would we build an index on the cover's color? Well, we've only got 5 different colors. And it's pretty likely that there will be at least one book of any given color on every shelf. If I use an index, I'm going to waste my time running back and forth to the index when the easiest thing to do would be, if I really wanted all of the green books, would be just to run through and start pulling the green books one after the other, because I'm going to have to hit so many indexes here that it would be a big time saver for me just to take my cart, go to the shelf, and start pulling out the green books. Using an index is a waste of time if I'm going to have to if I'm going to return 20 to 25% of the entire collection, it would be easier just to go from start to finish. You run into this when you say, should I build an index, for example, on zip code? How many zip codes are there in Frisco, do you think? Answer, I don't know. I don't have a clue. But I'm going to guess probably 20 in the whole town. Therefore, on any given search, if I say, I want all the people from zip code 76209 or whatever they are in Frisco, I'm going to get about 5 or 10% of the entire population of Frisco. And this does not make a good index. I want an index that returns a very small number. For example, the title. If I search on the title, it's okay to get more than one book of that title, but I don't want to get 10% of the whole library. Again, the authors write different books. I have authors that have the same name. Again, I have subjects that are the same across books, but I don't want to end up retrieving 10% of the library. Example 3, sometimes books come with abstracts. The one-page synopsis of the book. Should we abstract that? Well, what information is on that index card? Of course, the title is. And if you put it on if you index the abstract, that means I would have to reproduce that whole one-page synopsis on each index card. And this we really don't like to do because it makes our index card is very big. So this guy, looks like it's in German there, but we put just the basic stuff that we need. This looks like the authors, STOLPE. I don't know. I don't read German. Okay, so I want something fairly small. So a title, yeah, that's good. A author's name, yeah, that's fairly small. A subject, that's probably pretty small. But an abstract, now that would be big. That would be at least a whole page. So I don't want to index that. Example 4, in example 4, for an index, I want a value that does not change very often. Consider your social security number. It doesn't change. That is definitely an index. There are definitely indexes built on that, you can bet. Why? Because there's only one person in the world that can have, or at least in the United States, that can have that. So that would be a good candidate for an index, but that doesn't change. You can't go down to the Social Security Department and say, I'm tired of my Social Security number. Can I have a different one, please? No, you're stuck with the one you've got. And so anything that changes is not a good index. Now, can it change? Yes, you can go in and update the index. But if you have to do that very often, it makes it a poor index. A field that will be constantly and rapidly changing, if it is. We prefer to index relatively static fields when we can. Now, can I index on a field that changes? Yes, I can. So we have 4, these are general guidelines for when we create an index. Creating an index is one of the easiest things to do, and it is also one of the most important. It will, if you do it right, you will vastly speed up your database. If you do it wrong, you can really slow it down and waste a lot of space. Okay. Don't index fields that are searched infrequently or small tables, wasting your resources. Okay, if nobody cares about that value, so what would I not index in our AP database? Let's say the vendor's database. Would I index the vendor's name? Probably. I mean, well, definitely I would index the vendor's name. Vendor ID is a primary key. As soon as you say it's a primary key, guess what? You built an index on it. So I'm going to come back to that later. Do not build an index on a primary key because there's already one built. Let's see, what would I not index? I probably would not index the city. I'm probably never going to try to look up all my vendors in Fresno, but maybe I do. And if I'm doing that very regularly, I might build the index. So I'm going to always be watching, how I'm using the database. But I want to set up something where I'm getting stuff, where I'm building indexes on things that I'm searching a lot. Do not index fields that have very few distinct values. And we call that in database, we say it has a low cardinality is the word there. So that would be like, do not index fields that, well, my example is zip code. So if I'm going to return 5% of the database, I only, if I specify one zip code in Frisco, I'm going to get back 5% of the people roughly. And that's a poor candidate. It's just you're doing better off not to fool with an index. But if there's an index built on it, the database is going to try to use it. Another one, probably the best example would be, I have a database of people and one of the fields is the person's gender. Are they male or female? Well, roughly 50% of the people are going to be male and 50% are going to be female, roughly. So if I specify that, if I index on that, and I search, I say, show me the females, I'm going to get back half the database, roughly. That's a terrible index. Okay? Just go through just start at the beginning and go through and pick them all out. It'll take a couple of minutes longer, but it's just, well, you'll get it faster without the database. Try to build indexes on fields that are as small as possible so we don't have to reproduce it, and we prefer static data. So these are our general guidelines. And now I'm going to show you how to build an index, and you're going to say, oh, that's easy. Nothing to it. But you put a lot of thought into what am I going to index? Now, think of a few examples, but if you build indexes that are poor choices, so since an index can make the database so much faster, some people say, well, just index everything. That's kind of the access approach. Build an index on everything. And no, definitely not. Go to the next. Here's a table. Create table, demo 1, demo 2, and. So the first one is the primary key. The second one is unique. By the way, I don't think we have seen this constraint yet. I can write a constraint demo unique. We don't do this a whole lot. In other words, I'm saying that demo 2 is unique, but it is not required. When I say something is the primary key, I'm saying that it is required and it is unique. Okay? You can just say that something has to be unique. We don't do this very often. Generally speaking, if it's unique, it is probably a primary key, but it doesn't have to be. First, the constraint is the primary key. unique cannot be null. Second one says it may be null. I don't say it can't be null. I just say it has to be unique. In order to insert a row, the system must search. And so anytime you have a primary key or a unique field, they're already indexed. Don't index them a second time. Once you say it's either a primary key or unique, that automatically builds an index. You don't have to index it a second time. Get the syntax? No, there's nothing to it. Let's say that we check then on this one, demo 3. It's going to be something that's important to us. We're going to be searching on it regularly, so it checks for that one. Let's pretend. I don't know how we knew that, but let's just say because I told you so. Let's say that it has very few duplicate values in it. Well, it can have some, but for the most part, you're only going to get 5 or 6 values. If I say where demo 3 is equal to 27, I'm only going to get 5 or 6 out of thousands. So it's probably a pretty good bet. Let's pretend that it doesn't change very often and that somebody really cares one way or the other. We're going to be searching on it a lot. So we tested it. I guess it doesn't change. It's just an integer. So that's a good candidate for an index. I'm going to ask you to apply those more than I am creating the index. Once we get it down and we decide we want an index on demo 3, it's a piece of cake. Nothing to it. It's this simple. Create index, demo index on demo table, demo 3. Now there are some other things that go into it. What kind of an index? There's clustered indexes, and there's indexes where the data are actually sorted by that, but they're sorted by the primary key. So we don't really care very much about, we just want an index, and it's going to build this real complicated search structure on that field such that we can find it very carefully. I think I have a slide in here on what actually happens, and it is a monster, this data structure that it builds. All you say is create index, give it a name, on, name the table. Yeah, there's a little more to it than this, but that's what does it. If I've chosen my field correctly, I speed up my data access by orders of magnitude. If I haven't chosen it correctly, I'm going to slow down my database and be wasting disk space because this guy takes up some space. Okay, let's review what we have to answer here. Do we care about that field? Frequently searched. Look for it a lot. And then I put another little hint in here. A foreign key is usually a good candidate if it doesn't fail others. It's usually a good candidate for an index. I want a field that is almost unique. It's kind of strange to say something is almost unique. It's either unique or it isn't. But it's okay if there's a duplicate in there, but I don't want lots and lots and lots of duplicates. A small, there's a word we should have, scalar value. That is what I like. A scalar value would be an integer or a character string. The scalar means it can be sorted, what it amounts to. Because I'm going to have to reproduce that value each time on each index entry. I like static data that do not change very often. It can change, yeah, it's okay. I can change it because I can go in and search through that index and make the changes in the indexes. But as I have to do that, again, it puts a big overhead on my database. And finally, I do not want a primary key and not a unique field. So I don't want something that has either of these constraints on it. Okay. If it meets these guidelines, then I would build the index. Pause here for a moment. Any questions? I'm going to, in the exercise, it says, what indexes would you create? And so, hint, hint, foreign keys that meet the rest of them. Some of them don't meet the second one. Okay, oh boy. This is I'm going to let you watch this video, but this is an index. A very, when you get to graduate school or in your senior level of a degree in computer science, they will probably make you write one of these things. And it is a monstrosity. You better be a pretty good programmer. And even then, it's one of those weed out programs. Basically, each node in this tree represents a disk page. So this is a disk page. It is 4,096 bytes. We just usually call it 4,000 bytes. And each one of these guys that has the arrow coming from it is a disk address, probably 32 bits or a 4-byte integer. Now, if I go into this guy and I'm searching for the value 19, I scan across the top page. So remember, a page is what I get when I do a disk read. You probably thought you could just read one integer from the disk, but you can't. It just, the reading from the disk is so expensive that it will never go in and just read one character. It's going to read 4,096 characters. And if you use them, fine. If you don't, well, that's fine too. So I probably got this root in memory, all of it. It probably gets put there immediately when I boot the database. And it's probably already there. And I scan through there looking for the value that I want. And what am I looking for? If I'm looking for something that is less than 19, I'm going to follow down this disk address. If it's greater than 19, I'm going to follow this disk address, and so on. So I'll have one here. If it's less than, if that were, say, 27, I'd follow down this one. And when I come into here, if it's less than 5, I'm going to follow this disk address. If it's greater than 5 but less than 13, let's see. If it's less than 19, I'm going to go this way. If it's greater than or equal to 19, I go this way. So it's greater than or equal to 19, I go here. Is it less than 24? I'm going to follow down this path. If it's greater than or equal to 24, I find it over here. If it's less than 30, it's in this one. If it's greater than or equal to 30, it's in here. I probably should have put 30 in there, but I didn't. So basically, I don't know how many entries I can have in here, but millions and millions of them. Well, let's see, I could have 4,096 bytes divided by 4, about 1,000 in each page. So this is 1,000 here. There's 1,000,000 at the second level and 1,000,000,000 at the third level. So I have indexed 1,000,000,000 integers, and I only have to do 1, 2, 3 disk accesses to find out where it is. Okay, no, I didn't mean to start that video. Each node in the tree is really a disk page. Each pointer is a page address, and the value is reproduced. And so there is redundancy in these guys. To estimate the disk needs, I talk about it here. Add up all the fields, and so I can estimate the size of the disk by just adding by figuring out how big is one record, and then how many do I expect? Add them up, multiply. The size of an index, I'm going to have to say how big is the key. And let's say we have 36 bytes. This is just a reasonable number. So if you had if your name were 36 characters, that would be so if you had a 36 with what 18 character name and you were using nchar, that would give you 36 bytes. So it's not unusual. So 40 bytes per entry, okay? Because we have the 4 byte disk address. Each node is 4 kilobytes, or about 4,000 bytes. So I can get 100 values into each node. So at the top level, I have 100 index values. Second level of the tree, I have 100 times 100, or 10,000 possible values at the second level. At the third level, we have 10,000 nodes times 100, so I can now index 1 million possible values on a 3-level tree. That means on 3 disk accesses, I can go straight to 1 million books. So it's a little bit like I go to one index, and that takes me to a second one, and that takes me to a third one, and now I can go through this huge library. Thus, a 3-level B tree, and unusual, would cost about 41 megabytes for this index. So that's the cost of that guy. So an index, that index on, if I had 1 million records, that cost me 41 megabytes for that index that was on the 36 byte field. That's not unusual, and I'm willing to spend that if I'm really going to use that. But it has to be something that I care about. If I'm not using that index, then it's just sitting there taking up 41 megabytes on my disk and slowing me down all the time. Comparing the time of access, let me just put it this way. How a disk access typically takes about, in a nice fast database machine, and you want your fastest disk access for your database machine. So you're going to spend some money to get a fast disk. You want your disk access to be about 5 milliseconds or so. You might hit it, you might not, but let's say you get 5 milliseconds. It's going to be an expensive disk. Most of them are about 10 or 15, but to get that, to find the record, to get straight to the record at 5 milliseconds in that, with that index, with that 3-level index, would take me 4 disk accesses. So I could find it in 20 milliseconds, or 2 hundredths of a second. If I didn't have an index, so let's see, 5 millisecond, worst time for scanning the entire table. If I did not have an index, it would be about 625 seconds if I had to go through the whole table. What is that, 100 minutes? 625 seconds, or something like 10 and a half minutes. Okay, do my math right. On the other hand, if I've chosen the index wisely, I will find it in 2 hundredths of a second. So here's something like 10 and a half minutes on the table scan, which if I don't have an index and I'm searching for something, the only thing I can do is go in there and search for it. Okay, for the most part, if you have a fairly small table, you'll find it in a few seconds, it'll come back. But if your queries are coming in at a rate of 2 or 3 per second, like at Amazon or someplace, you better have some good indexes. Otherwise, they're going to start stacking up. So I can't afford to spend 10 and a half minutes on each query. Okay. This is the important point. Let's review the important point. The ones that will be on the final is, when do we index a field? Frequently searched. If it's a foreign key, you consider it's a candidate for an index if it meets the rest of them. We index a field where the values are widely dispersed, or I say pretty much unique or almost unique. SSN's good. Address is pretty good. Phone number's usually okay. They usually work like that. Zip code isn't good. Zip code returns lots of values. Address would probably not be good on the next one. We like small fields, and addresses tend to be kind of big. So SSN is good. Phone number is okay. Address would meet this widely dispersed one, but the number 3, it would probably fail because it's too big. We like data that don't change. Remember that B+ tree up there, this guy? How would you like to have to go in here and change this thing? It is a monster. Trust me on that. So we don't like changing it. We like data that do not tend to change very much. Let's see. Do not create indexes on a primary key or any field that is unique. Okay, well, this is the quiz. Let me look at the indexing assignment. Here I give you all of the lines and arrows and everything. This, by the way, this denotes the dot denotes a primary key, the one side of a one-to-many relationship, and the crow's foot indicates the many side. So one vendor ID to many invoices, one invoice ID to many invoice line items, one general ledger account number to many invoice line items, and also many vendors. Terms, one term to many invoices, one term ID to many default terms IDs. And what do we know about the use of these tables? I'm going to let you make some assumptions about the use of these tables. But you have to tell me what those assumptions are. So if you're going to build an index on something, creating the index, remember, is very, very easy. It's just create index, you give it a name. By the way, don't forget to do go. Create index. Let's say you want to index the vendor name. I might index the vendor name. Vendor name index. And it's as simple as, go back here. I think it's on the one just before this. Okay, this creates the index. Create the index, you give it a name, on, give it a table, and a field. That's all there is to it in terms of syntax. So this isn't one that you have to sit here and worry about, what do I enter join to what? It is possible to create an index on more than one field. Many times you will do that. Unless it's a two-field primary key. In that case, you wouldn't. But if I have something that I have lots of pairs and I care about the pairs a lot, I might index the pairs. Now I can say on demo table, demo 2, comma, demo 3, I could index these two guys together into one index. And then if I specified a lot where I was looking for them as a pair a lot, so if I were going to index the vendor name, for example, the vendor contact name, I would probably index the first name and the last name together if it met my criteria. And basically, I'm going to ask you, what criteria, how are you thinking when you do this? So if you create the index, let's say I want to create an index on invoice total. Why do you want to create an invoice on invoice total? Hint, hint, I would not. Why would you create an index on vendor city? Well, you're allowed to make something up because we search on that a lot. So I'm going to accept that, but I am going to ask that you, in with it, say why you chose that one. Now, how many appropriate indexes on the database? How many do I want? I'm going to go ahead and say I think 5 would be appropriate. I would create an index, for example. Why would I create an index on vendor ID in the invoices table? Yes, that's a question that I'd like to hear an answer to.
Because vendor ID in the invoices table is a foreign key.
That's probably the biggest reason right there. It's a foreign key. And then I would also say, well, just go look at it, go look at the data, and you'll see that there's not a whole lot of duplication in it. There's some. I'll have various invoices for a vendor ID, so I'll have some duplicates on vendor ID, but not a whole lot. And the fact that it's a foreign key means I care about it. It's not very big, just an integer, so it meets that. It's not going to change because it's a primary key, so it's going to meet that one. So it meets all of our criteria. And the fact that it's a foreign key says I'm going to be searching on it a lot. So once I say it's a foreign key, that means that I'm really going to be using it a lot, probably. So anytime you have a foreign key, what foreign key would I probably not index? Consider the terms table. And we go to the terms ID, and the terms ID in the invoices table. So I go to the terms ID of either the default terms ID or the terms ID in invoices. And if I were to take a look at that, databases, tables, I'm going to go to let's look at the invoices table. Edit 200 rows. And let's take a look at the terms ID. Notice the terms ID 33333. Here's a 1. 333333. 1, 2, 3, 4, 1, 2. I've only got 3 or 4. I've only got 4 of them. I guess I got 5 of them. There's one lonely little 5 down there. But this is one that fails, even though it is a foreign key. It fails because it's got too many duplicates in it. So I'm not, if I want to search on where the terms ID is 3, I would do a whole lot better just to go plow through the database. Chances are pretty good that I'm not going to search on that very often. Making any sense?
Yes.
Okay. So this is a pretty easy one, it's 40 points, but I do want to see why. So as you create it, so you're going to say, you know, create index, the query, use AP DB. Always have a go. Anytime you say create, always spell create right. Create index. What will I call this one? Vendor there's some people, sometimes people, instead of saying index, you will see people will frequently abbreviate it. It is good practice to name things in such a way as you know what it is. So we're starting to see different objects now. And by the way, you end up with a lot of indexes if you in a working database. And I will usually either put at the beginning or the end of my name something that tells me what it is. For example, if it's a table, I will put TBL. If it's a view, I will put VIW. If it's an index, IDX, and so on. That's something that you will develop, and you will see people. Lots of people will use this. It is a good practice. So create index, give it the name. On invoices, vendor ID. Go. Why did you do that? Okay, this is pretty easy. So when I execute this, most of the time you don't have any errors on that. Most of the time it completes successfully. You drop an index the same way that you drop anything else. If you try to create an index, it's going to stay there until you drop it. So if I were to go over and over to my tables on the invoices table, I probably, if I'm going to go look over here, I should probably close everything, and then refresh. Now open it again, because sometimes unless it's closed and reopened, it doesn't refresh. So I open the tables, and I look at the invoices table, and here is the indexes. So I can go in here and I can find the indexes, and here's the index, vendor ID. Showing me the properties of it here. Now, a clustered index, when you create a clustered index means that your data are sorted by that index. So the primary key is usually always, almost always, the only clustered index you have. Think about it. I can't be sorted by more than one value. Only thing I can do is if it's sorted by the primary key, it can't be sorted by the terms ID. Or the vendor ID in this case. So this one says it's non-unique, non-clustered, as it probably will. It is if I created one on invoices, it would be redundant. Now I can drop this index. So I can drop it with my SQL, or I can drop it over here using the Object Explorer. If I highlight it and I say delete, it will delete it. Or if I say drop index, vendor ID IDX, that will also do it. Goodbye. Must specify the table name. I'll have to look at that. Drop index. Is it on? Is it the on? I'll have to look up the drop index. I usually do it over here. If I just say delete right there, no. If I highlight this and I say delete, highlight, delete. Okay. And that goes away. That's the way I generally do it. And I'll look up that drop index. Guess I might as well do it now. Why would you drop an index? I'm going to talk about that in a minute. Drop index on, so it's just on the table name. Okay, so I think that's all it needs. So if I create it, then I should be able to drop it thus. Yeah, okay, so it does not take the field name to drop it. Why would I drop an index? Remember, I told you that indexes are very expensive. Indexes speed up searching very, very much, very well. Indexes slow down inserting and deleting and maintaining the database. So an index is a big help for searching and a big hindrance for inserting. An index is a very complicated data structure, and if I drop it and recreate it, now I don't have any data in these tables really, but if I have a million items in a table that are indexed, it's going to could easily take me 25 or 30 minutes to create that index. Wouldn't be unusual at all. But sometimes it is valuable to drop the indexes. The only index that I am not allowed to drop or disable is the primary key. Primary key has got to be there, but the rest of the indexes, I'm free to drop them if I need to. Why would I drop an index? Think about the college. What are we doing right now at Collin College that opens today? Hint, hint, registration. For next semester, right? Everybody says, yeah. What's happening? Everybody's suddenly started to add classes. And you get the classes and you try them in there, and so you add them, and oh, that class didn't make, and the other class I wanted to take didn't make, and then they changed my hours at work and all that jazz, and you're changing around a lot of stuff, and that's very expensive for the database. So what they do right about now, they go in and they drop all of their indexes, and they say, I'm going to pay the cost and it's going to cost me more to do a search on a class, but since people are so quick, are inserting and deleting so quickly, that we're just going to go ahead and take that cost to allow to make it simpler to insert and delete and make changes. Then comes the 12th day of class. You are now in the class. You're in the class. If you drop before the 12th class day, you were never in that class as far as the database is concerned. After the 12th class day, you are in, and that's when they build the indexes. So they go back in and they create the indexes again. And so that's, excuse me, I'm about to lose my voice here. So I think I'm going to wrap this up here. My throat's getting sore. But we're going to create, let's say, what did I say to do? How many indexes? I'm saying let's do 5 indexes. Okay, it says create appropriate indexes. Let me edit that. I'm going to put 5. I think it'll support 5. And then in a comment, explain why. Explain why you created each one in a comment. Oh, let's see. Today's the 13th. Oh, there you ought to be able to get this one by the 20th. I don't want stuff going over Thanksgiving. I'm going to make it the 20th, but I'm not going to turn it off. If you work on it over Thanksgiving, that's okay. Questions? Lost somebody. Who'd I lose? Okay, you'll find that the coding part of this assignment is just almost too simple. So the part I'm going to be grading mostly is why did you make that choice? And remember, you are allowed to make things up. If you tell me what you're making up, if you tell me that this is important, well, why is it important? Because I say so. Then that's a valid reason. Tell me why it's important, though. I mean, you use it frequently. How do I? Well, I don't know that you do. Well, you know that you do. See, I'm willing to take your scenario. So you get to create this scenario, right? Okay, I'm going to wrap up there. My voice is fading. And all the people said, okay, I'm going to end the recording now.